Yeah, so my name is Yi-Hsin Liu, and I'm working at Dartmouth College. And today I'm going to talk about magnetic reconnection, especially with application at Magnetopause. And yeah. So why it matters? So let me start from telling you what is magnetic reconnection. So the most basic picture we have here. So we have an anti-parallel B field, okay, pointing in different direction. And imagine that we have inflow in the first place. This inflow will bring in magnetic flux because the flux is frozen into the plasma. While the field line is close enough, usually it's within a plasma kinetic scale, like a gyro radius or inertial scale, and the field line can break. And you see this newly formed field line have a large curvature, right? And the field line and the plasma have a special property that it has tension force. So if you have this high curvature B field, you want to shoot out the plasma. So it acts like a slingshot. So once plasma is being ejected out, then the pressure in the center will drop. And therefore, due to the pressure balance, this will suck in more inflow in plasma, bring in the magnetic flux for reconnection. Therefore, reconnection is a self-driven process. Okay? And it's a very efficient mechanism that converts magnetic energy to plasma kinetic energy. And this is our application. Here's the sun, while I smile. And here's our Earth. It's very tiny. And you know in Earth we have many fields. So it's dipole field, right? And here it's more like a dipole. In this side it's like a stretch dipole. Because the rain pressure in the solar wind will make this dipole stretched. So as I say, I have a solar wind, right? Solar wind is a supersonic, and it breaks away from the sun and encounter this magnetosphere will need to go through the supersonic to subsonic transition, and this will form a bow shock. And downstream of bow shock is a magnetic sheath. So magnetic sheath. And you see the B field here is anti-parallel compared to this one. They are pointing in different directions, so reconnection can occur. The same thing happened here in the tail. So you have B field is pointing in opposite direction, therefore reconnection can occur. And once this occurs, they can release the energy that built up in the magnetic tail, and the particle associated with the reconnection will trace field line back to the north and the south pole. This will form aurora. Okay? So this has something to do with the magnetospheric storm and the substorm and cause aurora. And this has implications for space weather because the strong geomagnetic storm, like the Carrington event in 1859, and then Quebec breakout, that can damage the satellite, astronaut, GPS system, and power grid on Earth. So it's important to understand the reconnection and also this kind of storm. Okay. Again, NASA recognized that in our magnetosphere is a very ideal test bed to study reconnection. We cannot do this in laboratory because the scale is too small, it's larger. The kinetic scale is small compared to the probe size. And also we cannot do it in astrophysics, of course. So however, we can launch satellite into a magnetosphere and measure what's going on inside this diffusion region where the field line break and rejoin. And this is a MAS mission that was launched 3 years ago, okay? So it consists of 4 identical spacecraft. So why do we need 4? Because we want to resolve 3-dimensional structure, okay? And this will lead a human in the first time we can really resolve the electron scale physics associated with reconnection. Okay, so it's at the end of the day, so it's nice to see this video. It's nice to wrap what I just say. So it's the MAS mission. So our way in the magnetosphere, and trigger the tail reconnection, and form the aurora. So it's nice to have visual. And the MAS mission appear. 4 spacecraft. 3-dimensional data, and 1 mission to study reconnection. Yeah, it's like a movie trailer, right? Very entertaining. And we are so determined, single-minded to try to unlock the mystery of reconnection. So it's, yeah. It's fun to working with NASA. So okay, let's go through something more serious. And the key change, why blue waters, and all accomplished to date. So in order to resolve this kinetic physics, the first principle way is to use particle and cell simulation, which is brute force method. So we solve the Lorentz force coupled with the Maxwell equation and self-consistently. And then we can resolve the probes that is the first principle description, which rich kinetic physics will be captured all over land almost. However, it demands considerable computational resource, not in 2D, but in 3D, it's really challenging. That's why we write a proposal to blue water. Okay, so in my project, what we want to do is trying to study a 3D nature of reconnection, especially how it differs from the conventional 2D picture. Okay, for example, here is a 2D simulation. Let me summarize again. Okay, so here's a diffusion region, the field line break, and you join here. And this is called an X line. It's white because it looks like X, right? And we have an ion diffusion region, which is broader. It's ion kinetic scale. And then we have an electron diffusion region, is the electron scale. So it's much smaller, okay? So in 2D, so please pay some attention to the coordinate I use, otherwise you're going to confuse in the next few slides. So the reconnection plane is X and a Z plane. Outflow is in the X direction, inflow, outflow, and Z is the inflow direction. And the outer plane direction is Y direction. So in 3D, therefore the X line is always perpendicular to the reconnection plane. It's always out of this 2D plane, okay, in 2D. However, in 3D, it can be different. For example, here is our original 2D reconnection plane. Now we extend to 3D. Actually, the X-line form at some angle is oblique now. It's not really out of this plane. Okay, it's not a well-defined plane now. And I want to study is a non-trivial question. There are lots of hypotheses. So some people say maybe the system try to maximize the reconnection rate, or maybe try to maximize the outflow speed, or maybe try to maximize the entropy production. Okay, and blue water gives us a first principle simulation to test this different idea. And I am going to tell you that we are looking for maximize the reconnection rate because we can show it. And let me elaborate more of what's going on here. So why can we have oblique? Why can we have the X9 in this angle? So we have B field in the X, Y plane. Okay, we are looking at X and Y plane. Remember, here is the X, Z plane. Now X, Y plane. So we have B field on two sides. Sphere side and the sheet side, 1 and 2. They can shear at some arbitrary angle, phi. And if you take a 2D cut like this and flip in this way, is XZ plane, then you have a in-plane B field that's anti-parallel. So you can have, in principle, once you see an anti-parallel B field, you can reconnect. However, you have some freedom to do. So we can do another cut like this, and also flip in this way. We see an anti-parallel B field as well. So the question will be, which plane does the reconnection prefer in a 3D system? It's not an easy question. And yeah, as long as we know the plane, then we know the X line, which is always perpendicular to this plane. Okay, then here's our first result using the blue water. Okay, it's an X here, the product B, C, D, E here is X and the Y plane. And here, this one is X and Z plane. It's a cut through the center here. Okay, so what do we do is that we initialize the X9 in the center, then it's sprayed. And have now freedom to determine the X9 orientation. So X9 is here. You see this intense current density is tracing its X line, and I have some degrees, minus 13 degrees. It's roughly the bisection angle that bisect the total magnetic shear. Here's a reference B1 and reference B2, okay? And we have, it's a well-defined measurement, and also can be seen in the reconnected B field. It's BZ, although plane, this plane, okay? And also we have the reconnection outflow in the electron and the ion. All suggest a similar angle. So it's minus 30 degree in this case. Then what can we learn from this? Just, okay, before I go into the 2D. So here's the time evolution of what I just showed. Initially it's in the center, then it's propagate out and form the X line. So we can do 2D as well, and the 2D actually tells us a lot. So we already know that in 3D it's minus 13 degrees. Then let's do 2D simulation at different oblique plane. Remember this oblique plane, okay, at different angle. And what I show is here is that reconnection rate, which is a reconnection electric field, okay, as a function of time. See how it's evolved. And at a different plane, have a different strength of B field and the upstream condition, okay, a different asymmetry. And we can measure reconnection rate. You can see that minus 13 degrees is the one that maximizes the reconnection rate. That's why I say that our system, minus 13 degrees, is actually trying to maximize the reconnection rate. Okay, so it sort of makes sense because reconnection rate is associated with the energy release. So by maximizing reconnection rate, we actually maximize the energy release. So here is another thing we did, trying to test the boundary condition effect. So remember we have this huge blue water run. Now we make the size, so in the y direction is shorter. And what we see is that the X line form, however, become very turbulent. Okay? So in comparison, what we had before is very laminar. And here it's very turbulent. So we conclude that this is due to the boundary effect. So small periodic systems often overestimate the turbulent level. And it's another reason that justify why we need to use flu water, because we have a lot of previous simulation by other group using small periodic system, and they see very turbulent reconnection. So here's a new thing here. Okay, other than orientation, and the stability, we're also trying to study how the reconnection spread. And this is important because reconnection in the magnetopause, once happen, can spread to the entire magnetopause. And this will determine the plasma entry rate from the solar wind to the magnetosphere, and also the global convection of a plasma around Earth. Okay, so what we do in the same simulation is that we measure the spreading. What I show here is the reconnection outflow. When the white dashed line here is the X line orientation. So we can measure how this signal propagate in this along this white dashed line. So what we see is here, time versus the spread distance along the X line, and it look like this is the spreading speed. Okay, so this is still a work in progress, and there are several candidates can explain the spreading. One is the alpha speed, maybe it's the alpha speed along this line, and maybe it's another candidate, maybe it's the current carrier speed, or maybe it's something else, and we're still trying to resolve this problem. Okay, so the third result is that actually in some cases the reconnection is really turbulent. Okay, and for example, is this determined by lower hybrid drift instability. And in this situation, the X-line definition will be hard. Okay, it's hard to really find what's the X-line. And my colleague at Los Alamos used this Lyapunov exponent of field line, which basically measures how the adjacent B field diverge from each other. Okay, and this, in principle, has something to do with the connection X-line. It's where is this singularity happen. Okay, so for example here, the maximum of Lyapunov exponent probably is the X-line in a turbulent system. So the final result here I show is that it's also important to study whether this turbulence in 3D X-line affect the reconnection rate. Okay, in 2D it's always laminar, and here is the two curves. Like 2D is the green one and the magenta one. You have these two give you the reconnection rate in 2D. And in 3D, how does the turbulence affect this reconnection rate is the question. And in our simulation, we measure that. And forget about the red one first. So here the blue one more or less trace the 2D result. So it's an important conclusion that turbulent 3D reconnection, turbulence does not really affect the reconnection rate in 3D. Okay, I come back to this rate curve. It's not an accurate measure because there is some cross field transport of plasma. Okay, the broader impact. So reconnection is a very fundamental plasma physics. So it can have application in the space science, okay, and MS mission, and also solar flare. So where the topology change enable this solar flare eruption in the CME. And also maybe the super flare in Crab Nebula has something to do with the reorganization of B field. And also in fusion device, for example, it's a B field here, trying to confine a hot plasma. Here is basically show the topology. You can see once you form this island, it's where reconnection already happened, and this will spell the confinement of the hot plasma. So it's bad. They don't like reconnection. Okay, in summary, so reconnection is a key process to release the magnetic energy stored in space, astrophysics, and stability plasma system. And the 3D nature of reconnection remain unclear. And then you need blue water to study this, for example. Yeah. And we use in the past 2 years, we use blue water. We have studied the orientation of 3D and concluded, give you evidence that 3D systems tend to maximize the reconnection rate. And also, we will study the spread of 3D X9, and we also study the laminar versus turbulent X9 and the 3D reconnection rate. And the broader impact for example, the direct application to the MS is that the orientation study might help interpret the 3D geometry of MS observation. Okay, thank you.